Section 3 in Chapter 20, Radioactive Decay and Half-Life. Now, we mentioned earlier that heavy elements, they try to decay very quickly to get back to stable nuclei. If you look over here in this graph, once again we have the number of neutrons in the y-axis versus atomic number in the x-axis. This is the top part of that band of stability graph. There are several, heavy nuclides that have larger atomic numbers than about 82, 83 are going to decay. They're radioactive. They're all going to decay. And the heavier the element, they decay in a series of decay, not just by a one-time thing, by one alpha particle, but they decay in a series or cascade. And the uranium-238, for example, has a Z of 92, and it decays. Look at how many alpha decays. The green arrow represents the alpha decays, and the red arrows the beta decays. Look at how many decays or what cascade it undergoes spontaneously or naturally to end up to a more stable isotopes. There are three families or three different cascades that include most of the radioactive elements in the periodic table, and those families, all of them undergo a cascade nuclear decay, and they end up pretty much with isotopes of lead because they end up back to the stable area, the band of stability area. These isotopes, so you have the first isotope that is called the mother isotope, and these are the daughter isotopes, or the daughter nuclides, and they undergo typically alpha decay, but some beta decay as well. Think about the fact that every time an alpha particle is given off, you're reducing the Z number by 2 and the mass number by 4. The beta decay, it just increases the Z number, but alpha decay does decrease by 2, the Z number by 2. So every time you have an alpha decay, you're decreasing the Z number by 2. We have three of these different nuclear cascade families. We're not going to talk in detail about all of them, but uranium is one of them, and all of them undergo these cascade nuclear decay and end up with an isotope of lead, which means that they're back to the band of stability graph, and that's what they're trying to get to. One thing that I do want to point out is this here. This is radon with a mass number of 222, and it's right in the middle of this cascade decay series for uranium. This is what actually makes radon kind of dangerous. If you have heard of radon being in the basements, you may or may not have heard it, but it is a problem, especially in the Midwest, because there are deposits of uranium in rocks all over the Midwest, and it decays naturally. It decays naturally, and it produces radon in its cascade series, which radon is a gas. It's a heavy gas, and therefore it deposits in basements. And if you're breathing it in, you're breathing in a radioactive gas that it will decay in your lungs. It decays into eventually lead. But because it is a gas and it's heavier than air, which means that it sits lower than air, which means that if we breathe it in our lungs, we have to be very careful, and that is why many houses now will have radon testing to figure out if the levels of radon in a house are larger than what they need to be, because as you breathe it in, it's going to continue to decay in your lungs, and that's not such a good thing. Let's talk about half-life. So every isotope that decays has a particular half-life. So what is a half-life? The half-life of an isotope is the time that it takes for half of the original isotopes to decay into a different type of isotope. So if I start out, for example, in this graph, I have the cobalt-60 that's remaining, and here I have the number of half-lives. So one half-life is 5.27 years. So if I start out with 100%, let's say a mass of 10 grams of cobalt-60, that's 100% at time 0. After one half-life, this is my first half-life, which is 5.27 years. After 5.27 years, or one half-life, I will have 50% of that original amount that I started with still remaining. 50% have decayed into something else. So the time of needed for half of the isotopes to decay. I started out with 100%, 50% of them decayed. So now, if I started out with 10 grams, if 50% of that decayed, what I have now left is 5 grams of the original material, cobalt-60, the original isotopes that I started with, because 50% or half of that decayed into something else. After my second half-life, half of my 50 is going to decay again into something else. Or I have 25% of that original 100% left, which means that I take the 5 grams and I divide that in 2 again, giving me 2.5 grams left. So every time a half-life occurs, I take the original amount and I cut it in half, and that is how much I have left. If after my three half-lives, I will have half of my 2.5 grams left, or 1.25 grams. And after another half-life, I will have half of 1.25 grams, and that's 0.625 grams. After another half-life, I will cut this in half and have 0.3125, etc., etc. So every half-life that passes, my original amount is reduced by half. Here I had 10, I cut it in half, I got 5. After another half-life, I got 5, divided 5 in half, I got 2.5. After another half-life, 2.5 is reduced by half to 1.25 grams, etc., etc. So a half-life is the time that is needed for the original amount of isotopes to decay by half. That's why it's called half-life. Life, how long it takes for half of the original amount that you had to decay into something else. Therefore, you have only half left after one half-life. I have made a video of how to work these types of problems with half-life. 4 different kinds of problems here that are asking for slightly different unknowns, but they all deal with half-lives. So take a look at how to do these problems and let me know if you have any questions. And this concludes this section of the section 3 of chapter 20, and in the next section we're going to talk about biological effects of radiation. That will be section 20.6.